More than 44,000 of them have been built. It is the most produced aircraft in history. And there is one thing it refuses to do. The Cessna 172 Skyhawk will not spin, even when a pilot applies full pro-spin control inputs in a deliberate attempt to make it rotate. The aircraft has a wingspan of 36 feet and 1 inch and a length of 27 feet and 2 inches, with a height of 8 feet and 11 inches. The wing area is 174 square feet, and the aspect ratio is 7.32. Those numbers place the Cessna 172S in the same general footprint as the Piper PA-28 Cherokee, which has a wingspan of 35 feet and 5 inches and a length of 23 feet 9 inches, though the two aircraft achieve their stability through fundamentally different wing geometries. The Cessna 172S's wing is a high-wing, strut-braced configuration built around a modified NACA 2412 airfoil. The NACA 2412 profile has a maximum camber of 2% at 20% chord and a thickness of 12% of the chord length. Those proportions produce substantial low-speed lift and a gradual, progressive stall onset rather than an abrupt separation. The wing incorporates geometric washout, a physical twist from root to tip, which means the root section operates at a higher angle of attack than the tips in any given flight attitude. The result is that the inboard wing section reaches its critical angle of attack and stalls before the outboard sections. From the 1970 model year onward, Cessna fitted the 172 with fiberglass conical camber wingtips, a downward curved tip geometry introduced on the 172K model. That conical camber shape modifies the span-wise pressure distribution at the tip, reducing induced drag and preserving airflow attachment at the wingtip region at high angles of attack. The practical effect is that the ailerons mounted in the outboard wing section retain aerodynamic effectiveness even as the inboard wing is stalling. The Cessna 172S's landing gear is a fixed tricycle configuration with tapered tubular steel main gear legs which absorb landing loads through flexion rather than through a hydraulic oleo system. Moving along the Cessna 172S's fuselage to the nose, the engine is a Lycoming IO36-L2A, four-cylinder horizontally opposed unit producing 180 horsepower at 2,700 revolutions per minute, a fuel-injected engine introduced on 180 when Cessna resumed production in 1998. Moving to the back of the Cessna 172S, the swept vertical tail and conventional horizontal stabilizer are sized well above the minimum required for control authority, a feature that provides the elevator leverage to resist uncommanded pitch changes during low-speed flight. The windshield is a single-piece unit with 4 cabin windows, 2 on each side. That wing, its airfoil, its washout, its conical camber tips, is the physical structure that carries the title question's answer inside it. The exterior is only the beginning of understanding it. Inside the Cessna 172S, entries through a pair of side-opening doors, one on each side of the fuselage, with a fixed step on the main gear leg providing access to the cabin. The cabin seats 4. Pilot and 1 front seat passenger side by side, and 2 rear seat passengers on a bench seat behind them. The Cessna 172S in its later production years came equipped with leather seats as standard equipment, alongside the Garmin G1000 avionics package. The front seats are contoured, energy-absorbing units certified to 26 times the force of gravity, with vertical height adjustment and reclining capability. Moving to the Cessna 172S's cockpit, the Garmin 1000 suite provides a primary flight display on the pilot's side and a multifunction display in the center of the panel. The G1000 integrates GPS navigation, a traffic advisory system, terrain awareness and warning, and weather data overlay capability. An optional GFC 700 digital autopilot integrates directly with the G1000. The controls are a dual yoke arrangement on a center column with the throttle, mixture, and carburetor heat, or in the case of the fuel-injected IO360-L2A, the alternate air control, mounted on a center console between the seats. The stall warning system is a pneumatic reed mounted in the leading edge, which produces an audible tone beginning approximately 5 to 10 knots before the stall speed. The cockpit of the Cessna 172S gives a pilot explicit notice of the approaching stall through both the pneumatic warning horn and the increasing control heaviness that accompanies airspeed decay. Every instrument in the panel and every aerodynamic signal transmitted through the airframe is pointing toward a specific operational boundary. Powering the Cessna 172S was the Lycoming IO360 L2A, producing 180 horsepower at 2,700 revolutions per minute. The propeller was a two-bladed metal fixed-pitch Macaulay unit, 6 feet and 3 inches in diameter at maximum. The Cessna 172S had a maximum gross weight of 2,550 pounds and an empty weight of 1,691 pounds in the 172R specification, the nearest certified figure from the FAA type certificate data for the airframe family, as the 172S figure varies by installed equipment. The Cessna 172S was capable of flying a cruise speed of 122 knots, 140 miles per hour at normal cruise power settings, and a never-exceed speed of 163 knots indicated airspeed. The range, with a 45-minute reserve at 55% power at 12,000 feet, was 696 nautical miles, 801 statute miles, enough to fly from Chicago to New York City non-stop with reserve fuel remaining. The service ceiling was 13,500 feet. With its 180 horsepower engine, the Cessna 172S could stay in the air for approximately 5 to 6 hours at normal cruise power on its 56 U.S. gallon total fuel capacity, of which 52 U.S. gallons were usable. The rate of climb from sea level was 721 feet per minute. The stall speed with flaps fully extended and power off, the VSO, or stall speed in the landing configuration, was 47 knots, or 54 miles per hour. The stall speed clean, the VS1, was not separately published in the Wikipedia source data for the 172S, but the 172R stall figure of 47 knots flaps down from the FAA type certificate is the confirmed baseline. The wing loading was 14.1 pounds per square foot, which is among the lowest in the 4-seat single-engine category. Those performance figures, particularly the low wing loading, the low stall speed, and the moderate power-to-weight ratio, are the numerical expression of a design that was built to behave in a very specific way at the edge of its flight envelope. What that behavior is and why it prevents rotation even under deliberate pro-spin inputs is the complete answer to the title question.